guys, welcome back. Today we're going to start lesson 6.5. I heard there's some volume issues, so I'm going to try to talk louder today. Let's see if I remember to do that. Alright, so today we are going to deal with the definite integral. And the notes that I'm showing right here are actually just slightly different than what you see. I'm using these because I like the pictures better, but they really do have all the same examples, so we should be fine with that. Okay, so the first thing, the page that you have, page 21 in your packet, is a great page that summarizes all the different techniques I'm going to show you today. But actually what I want to do is just kind of skip over this page right now because it's not going to make much sense until we go through the process a few times. If you could just not even look at your packet, just turn to page 22 and let that sit on your desk for a minute. What I want you to do is look only at the board here. There's some things going on. You're going to start to see some crazy notation. This is called a Riemann sum. Right here, this LRAN, that stands for left rectangular approximation method. Honestly, you don't really need to know what that means, but just in case you see it in your notes, now you'll be able to have some idea. And if you look at my pictures here, what we're going to do, an integral is the area under a curve. And, we've been practicing computing an integral, but you really didn't know what you were doing until now. So if you look at the curve here, we can see that we have some blocks underneath. And today what we're going to do is talk about different ways to draw our rectangles. This is a left endpoint approximation, so the left RAM that I just was talking about. And you can see what I'm doing is I am breaking up blocks underneath, some above, by my curve, just to start to approximate the area under the curve. So you can see that this is not going to be a precise estimate because here we're missing some space here, and over here we'll be overestimating in this portion. But the thing that we're talking about is that when we're drawing our rectangles to compute this today, you're going to need to pay attention if we say left versus right or midpoint or trapezoidal, because if I say left, then what you're going to do is you're going to draw the height of the rectangle according to the left-hand side. So this rectangle, when I go up, it hits the curve here, and that's the height of this rectangle. This rectangle, as I go up, so this is the left-hand side of the second rectangle, you can see that's the height I draw here. Okay, versus, just you might be thinking like, well, I don't understand the difference. Well, if you look next to this at the right, so now you can see if I choose to use the height from the right-hand side, how much higher this bar is versus this bar, okay? And you can see that that's what's going on here. So depending on if I say left or right, you're going to have a different picture. Some things will give you overestimates, some things will give you underestimates, and we'll go through that. Okay, so that's why I like these notes, because I think that the picture really shows you what's about to happen here. Here's another picture for you. Okay, it's basically the same thing there. Sorry. Okay, here's a picture for the midpoint approximation. Okay, so for the midpoint, again, don't worry about this too much. I will show you where that all comes from. But this it's exactly what you would think. You go to the middle of your rectangle, and you go up to the height, so the height where it strikes the curve, and that's the height of your rectangle. Okay, so that's a little bit more accurate, you can see. And finally, we have our trapezoidal, and we don't have a picture of that one, so when we get to the trapezoidal, I'll draw that out. Okay, so let's get right into our examples here. It says, using 4 intervals, find the area under the curve for the function x squared plus 1. So the first thing I want to do is draw the function for you. Okay, I'm going to draw first a zoomed out version of x squared plus 1 because we should all know this, and then I'll draw a zoomed in version to help us compute. So everyone in our room should absolutely know that this is a parabola that's been translated up 1 unit. So we're going to draw this picture. Okay, once I have that drawn in there, we can think to ourselves, well, if I sub in 0, I get 1, so we know this ordered pair is 0, 1. If I sub in a 1, I get 2. So at 1, this height is sitting at 2. So my picture's not very accurate here, but let's call that 2 for now, and that's 1. Okay, so at this point, though, like I said, I am going to zoom out. What they're saying here is we're going to find 4 intervals under this curve, so under our curve, on the interval of 0 to 1. So they want me to focus only in this region here. Let me get a different color to outline that. Okay, so they want me to focus in here using the left endpoint approximation method. Okay, so another key thing was the 4 intervals, so I'll circle that. So that's what we're doing right now. We're going to find the area under the curve that I highlighted in blue. So now let's draw a zoomed in version of this so that we can actually break that up. Okay, so again, this point here is 0, 1, and then we'll make this 1, and this height would be 2, we said. Okay, so there's my points, there's my curve, and that's the area in blue that we're looking at. Okay, so now it says to break this up into 4 intervals. So naturally, halfway between would be a half. Then we would get 1/4 and 3/4. Okay. So this is how we're creating our rectangles. Okay, since it says that we're using our left endpoint approximation, we need to go to the left-hand side of each block and draw the height. Okay, so again, I just go up to the height, I find that side, and I draw my height underneath. So you can see here, if I start to find the area of each of these 4 pieces, I will be getting an underestimate because there's going to be space. You can see the best view here. There will be some space that we did not account for, and that's okay. That's what we're doing today. So what we have to do, well, first of all, I guess I should back up. I went through and I looked through this and said, you want me to break this up into 4 sub-intervals, they're called. So I just broke them up and I said divided by 2 and so on. Part of our formula says to take the highest piece, so 1, subtract the lowest, which is 0, and divide that by the number of intervals they're asking for. So you can see if I do that, I get 1/4, and that's the width of each of my rectangles. Okay, so again, you just take your highest piece minus your smallest, divide that by the number of intervals, and that will get you your width of them. Okay, so now that I have that all set up, what Mr. Obst recommends, and I do think it's kind of a nice idea, is he does all of the work beforehand, and then he just does the number crunching at the end. So I wouldn't erase this, but I don't have a lot of board space, so I'm going to just do my work here. So you just write yours right underneath, please. What we're going to do is we're going to find the values of each of our rectangles. So we're going to find, and let me highlight this in blue, we're going to find the area of this rectangle first. And we all know the area of a rectangle is length times width. So if we know that this is already a 4th wide, we basically need to know how high is this. And you can eyeball that up and say 1, right? So we're going to go through and we're going to write f of 0. So the height at 0 is equal to 1. And then we're going to go through and we're going to go and list all of our functions, the heights of each of our rectangles. So this one, that's the height of the first one. Again, another color here. Okay, let's focus on the orange one. So f of 1/4 is equal to what? Well, I want to know the height of that. So if I want to know f of 1/4, I simply sub it into my function. Okay, so 1/4 squared plus 1. That will get me 1/16 plus 1, which would get me 17/16. Okay, so there's the height at 1/4. And we'll continue to do this so that we have all of our heights all lined up for us. So let's do f of 1/2, f of 3/4. And that's it for this example, because if I look at f of 1, that's not the left side of a rectangle, so I don't need that right now. Okay? I am going to do that right now for this example. Maybe I'll put like a not needed for this problem. Only because we're going to do this exact same problem 4 different ways. We're going to do it left, right, midpoint, and trapezoidal. So we might as well find it now when we're doing the other number crunching. Okay, so take a minute, please. Go through and find these answers, and then we'll see if yours match up with mine. Okay, again, you're subbing that in to the function. So if you could pause the video, figure them out, and then start it, that would be great. Okay, so starting back up, f of 1/2, I got 5/4. F of 3/4, I got 25/16. Okay, and f of 1, again, not needed for this problem, I got 2. Okay, so again, this is just the work so that we can now find the area under this curve. So, again, very logical with this lesson here. You could try to memorize the formulas on the first page, or you could just make sense of this. If I want you to take the area of each of these rectangles and add them up, what math would need to be shown? Well, wouldn't it be the area of the first one, which is length times width? So what would that be? Let's see, we would have 1/4 wide times the height, which f of 0 is 1, plus 1/4 wide for my orange one, times the height, which f of 1/4, we got 17/16, plus 1/4 for our third rectangle, times the height of the left-hand side, which was 5/4, and I'm running out of space for you to see. I'll just add it here, plus 1/4 times, and then we're on our last rectangle, the height of f of 3/4 is 25/16. And I am more than okay with you using a calculator for this to compute. Now, once you have this, basically you can use a calculator to add this all up. But I do want to note to you, if you're consistently using a fourth, couldn't I rewrite all of this jazz like this? 1/4 times 1 plus 17/16 plus 5/4 plus 25/16. All I did was factor out that GCF of 1/4. Then I can use my calculator to just quickly add up my fractions, multiply that thing by 1/4, and in the end, you should get, as a fraction, 39/32, which is approximately 1.219. Okay? And you can talk to Miss Craig about what she would prefer. Last year, what I did was I offered extra credit if somebody worked through this by hand and used no calculator and got an accurate fraction. If they used a calculator and got the decimal, then they got full credit. I told you before, it's like going the extra mile. This is right and this is right. But this is a little bit harder, so if you want to go the extra mile and do that, then I awarded last year's class like a point for each one that they did that for. Okay, but I would like to see the work regardless, please. I would like to see the work of this stuff over here, for sure. And even this would be great to see. Show me where you're getting this from, especially because it is so easy to hit the wrong button on the calculator, get the wrong answer, and you can lose 2 points or you can lose 10. It's up to you. If you show this, you'll lose 2 points if you just hit something wrong, versus 10 if you're doing everything in your head. Okay, so always remember, show your work when you're doing heavy calculator stuff. I will remind Miss Craig this earlier, but I guess Jasmine and Kel, if you could ask Miss O'Donnell for the calculators for this section, and then of course for the test. I'll email her and make sure that that's okay. But that would be great. Okay. Okay, so that's the left sum graph here, and that's our answer. So let's move on to the right one now. So again, we're going to use the same picture, and we're going to use the same work that I just erased. Okay, I am going to redraw each time because even though it's the same function as far as x squared plus 1, of course our rectangles will change as I change the way I want you to draw it. Okay, so moral of the story, you'll probably want to flip back to that page to get some of the values we just found. Okay, so same question. We're going to, again, let's sketch this for ourselves. Please just draw the zoomed in version. So we're going from 0 to 1 again. Our parabola looks like this. Okay, I guess I'll do this. That height we're calling 2. That height we're calling 1. Again, they want these broken up into 4 sub-intervals. So we have our 1/2, we have our 1/4, we have our 3/4, and our 1. Okay. Okay, so this time, since they want us to use the right approximation, what we're going to do is take our right-hand side. So I'll start over here, and you'll see that this time I'm going to be above my curve a bit to draw that in. And again, here's the right-hand side of the rectangle. So we'll be here. The right-hand side of the next, and the right-hand side of the last. So this will have an overestimate, you can see, because my rectangles are actually going above the curve and actually all of the pieces here. Okay? So once again, we'll just go through. We already know the width is 1/4 from, again, above, but let me show you that work again. We have 1 minus 0 divided by 4, getting us a 1/4 width across. So that's nice and simple. And then we're going to go through, and we need to use our different heights. Okay, so this time, again, let's just write it this way, where we're going to factor out that common 1/4. And what I would like to see, we've already done the work before in our other problem, but you can see the right-hand side. Do you see I won't be using 0 this time? That's a left-hand side of a rectangle. It is not a right-hand side, so I don't need that information anymore. I will need f of 1/4. I will need f of 1/2, 3/4, and 1. So let's write that here.